All right. Thank you for your patience, everybody. Our next presentation will be from two leaders who would come from Ford who are coming on stage to share about their progress when it comes to digital thread. One second. Hi, Pramita. Hi, Helen. Welcome to the stage, and thank you so much for joining us this afternoon. We're very excited. I am personally very excited about your presentation. For a few years, I've been in the additive manufacturing space, and my work has focused on really production, taking it from piloting and scaling to production. And there has been questions and concern about digital thread. How do we manage everything? And I'm very excited to hear your talk today. And in the way of introduction, we have on the stage right now Ellen Lee, who is the technical leader at Ford Motor Company, and she's the additive manufacturing technical leader. In addition, we have Pramita Mitra, who is the group leader, IoT and blockchain applications at Ford Motor Company. They're here to present their work titled Securing the AM Digital Thread for Promotion for Production. Whenever you're ready, please take it away.
Great, thank you so much. It's a pleasure to be here today. I think Pramita is going to share the presentation, and then I'll kick us off once we get that on the screen. Thank you so much, Pramita. Thank you so much, Addie, and the organizers for TIPE. It's such a pleasure to be here for the third time in a row for me. TIPE is one of the things that I look forward to every year. It's such a great virtual conference. So as Addie mentioned today, Dr. Pramita Mitra and I will be presenting a research pilot that we did focused on securing the digital thread for additive manufacturing production. So if you go to the next slide, this just shows a roadmap of what our presentation will be today. First, we'll level set on the importance of and the use cases of additive manufacturing for the automotive industry. And then we'll talk about a future state for using additive manufacturing in a distributed manufacturing scenario. Then we'll highlight how this distributed model and our dependence on the digital thread highlights the need for cybersecurity. And then before I pass it on to Dr. Mitra, I'd like to touch on how we connect the digital and the physical twins that's essential for this. Then Pramita will talk about blockchain, a little bit more about what it is and why we're using it here. And then she'll go into some of the details about the research pilot, as well as the results, and finally conclude with some lessons learned. So the next slide. So many of you have seen the slide before, but I think it provides a great overview of why the automotive industry, and Ford in particular, cares about additive manufacturing. So the unique attributes of additive compared with traditional tooled production that we use for mass manufacturing in the automotive industry and other manufacturing verticals, namely the design freedoms that we can get through AM, as well as being able to produce parts without a mold or a tool, lead to some really important benefits that you see here. We can quickly iterate through designs, both in the design as well as the validation, engineering validation stages. We can make very complex geometries, like some of the things that you see here on the screen, that enables us to do things like integration of function and parts, which allows fewer operations and a simpler supply chain. In many of these cases, then we can also improve the performance or have unique performance that we cannot otherwise get from conventional means. But above all, what we in the automotive industry look for is cost reduction or creation of value. So if we go to the next slide, It's these business efficiencies and engineering efficiencies that we're provided with that you from those benefits that I just talked about that lead to these being the primary use cases that we see value from additive manufacturing. And these are very similar or typical to ones that other additive manufacturing users would have. For the past 30 to almost 40 years now, we've been using additive for prototypes and engineering validation. And we continue to see more and more significant savings as we increase or advance the technologies and make more functional materials that allow us to eventually eliminate the need for prototype tooling. On the manufacturing floor, we continue to make progress in seeing value and cost reductions by printing things like prototype tooling or production tooling, jigs, fixtures, and lift assists as well. And in addition to, in many cases, having better quality using these printed tools, we're also importantly improving the ergonomics for the operators. In the next category for performance, this is really the sweet spot for additive manufacturing, where we can increase the performance or have unique capabilities that really helps us to differentiate our products from our competitors. And so this area of performance and customization is really prime for our performance lineup. But the category that we focus a lot of our attention on in the research organization is can we get to high volume scaled production using additive manufacturing for our parts? And here we focus on a lot of the technology gaps that exist before we can get to that point. And one of these technology gaps is cybersecurity. So if we go to the next slide, as we continue to move forward into this state of scaled production using additive manufacturing, not only will we see digital parts and products be manufactured at scale, potentially in a vertically integrated scenario, or also in a distributed scenario where parts may be made by our suppliers or dealers on the premises, on demand, reducing transportation, reducing inventory, and really helping speed to market. So you see, though, in the schematic that in this distributed scenario, we have a fully digital process flow. And so there are very highly sensitive data that are transferred from one stakeholder to the next, and we need to ensure security at each of these transfer points. So what that means for scale production, this is important for quality. Not only do we need to understand the provenance for each part before it leaves us, but we also need to make sure that all of our downstream partners are also printing the right things with the right materials and processes at the right time and the right quantities. And furthermore, as we move more and more towards production additive manufacturing, for continuous improvement and iteration of our products. And so we need to be even more meticulous with version control. So each of these iterations may have only minor changes in, let's say, in the process itself or in some of the quality capability steps, but they may have significant performance downstream in the quality of the part or the function of the part. And so all of the digital assets need verification at each step. This type of traceability ensures that no errors are propagated down the workflow. Now, when we consider the distributed scenario, a big concern is counterfeiting. So this can impact not only our business and bottom line, but importantly, quality, safety, and performance. So stolen files or parts, especially if they're scanned and reverse engineered, for example, may not have or will not have the necessary information, details, processing requirements to meet all of the function. And if such a part were to make it onto a vehicle and failed, it could have serious safety implications for the customer, and importantly, have severe ramifications about our reputation as Ford Motor Company. So if we go to the next slide. So we wanted to answer this question in the problem statement. How might we create a real-time and verifiable solution to secure the digital workflow of distributed additive manufacturing, addressing counterfeit part detection and quality issue tracking? And so our solution was to develop this research pilot that we called the AM Part Passport. This pilot was performed in collaboration with Identify 3D. And it was designed, we designed and developed an integrated Internet of Things and blockchain-based solution. So if you look to the right side, we defined these steps in the workflow. In the design phase, we generate an encrypted digital supply item, or DSI. And specifically for this pilot, we start the design phase after the initial engineering and design verification steps that are obviously very important in the additive manufacturing workflow. But here, we're just capturing this part for the need for cybersecurity from this part. So the DSI essentially starts out as the digital tool or mold for the part. So it includes all the CAD geometry, G-code, if necessary for that process, printer details, parameter sets, materials, and any quality control or documentation that's needed to ensure production of a good part. In the next phase, distribution, this DSI and license are securely moved down to downstream partners, and then to the print phase, where the DSI is decrypted and processed. And during the print process, as well as the post-processing steps, data are collected from the machines and processes and used for quality control. And all of that information and data remain with the digital part. And then finally, in the use phase, the physical part is tracked as it moves through the supply chain to the customer. So at each of these steps, as you'll see when Permita steps through the details of the pilot, the events and data are all recorded, and each of these process steps need to be authorized through this tool developed with Identify 3D using blockchain. So in the next slide, I first wanted to touch a bit on connecting the physical part with its digital twin. Doing so is critical for traceability, part authentication, and counterfeit detection. So for QC, we need to ensure that the physical part is correctly connected with its digital twin and all of the data in the full workflow. So a common approach to do this is to add a taggant. This can be either a physical or a chemical taggant. Examples of a physical taggant is an RFID tag or a printed QR or barcode. Chemical taggants can include some trace chemical or particle that's added to the material itself that can be detected by some sort of spectroscopy. Or we could even think about including some sort of secret design that's in the interior of the part that can be detected in order to authenticate a real part. So some of the drawbacks, however, of looking at using taggants are one, the cost. So in the case of an RFID tag, if we're looking to go to high volume production, this can be a really costly solution. In addition, things like QR codes and barcodes could themselves be counterfeited. And adding chemical taggants or trace particles could potentially impact the downstream recycling or contaminate a recycled stream of the material at the end of life of these parts. And they can potentially, any of these approaches could potentially alter the performance of the part if it's not done correctly. And so the preferred approach would be to have a contactless method that uses some intrinsic natural feature of the physical part as a unique identifier or fingerprint. So for example, some researchers have used a signature sound associated with the mechanical motions of the printing to associate with each part. But in our study, we chose to use computer vision to detect some surface signature, or texture for its digital fingerprint. So in the first phase, we would use computer vision to register the part with its unique signature. And then this is aided by an artificial intelligence or machine learning technology that quickly helps us to authenticate the part, to look through the database to match it with a registered fingerprint. So if we go to the next slide, I'll just finish up this section before passing it off to talk about the work we did to develop this contactless method. So we chose to develop this method using surrogate parts and geometries that are pictured here that include geometric parts, full tensile specimens, as well as other and production level parts. These were done with both extrusion-based parts that you see here, as well as looking at vat photopolymerization parts and powder bed fusion polymer parts. Because the visual method or fingerprint that we used is really based on surface appearance, we needed to probe whether the post-processing steps and field exposure conditions had any effects on the efficacy of the authentication. For the polymeric materials we used, we imagined scenarios that might affect the appearance, including things like vapor smoothing for a post-processing step, as well as UV exposure for outdoor use, or heat aging if it's in a hot environment. And so some of our initial findings showed that for some of the materials, we looked at UV exposure could have some impact with a risk of false positives. Heat aging for these types of materials resulted in successful authentication. But as you can imagine, for things like vapor smoothing, if we're really changing the texture of the part and reducing pores and so forth, a lot of these appearance-based things would not remain to be authenticated. So I'll stop this discussion here so that we can move on to some of the details of the pilot. So go ahead, Pramina. Would you like me to share while you're speaking?
Sorry, I just needed to come off mute. That's why I stopped sharing.
Oh, okay.
So I hope that you guys can all hear me and then see the slides as well.
Yes.
Awesome. All right. So thanks, Ellen, for the great overview of the actual application as well as the physical to digital connection piece. I have the pleasure of actually discussing the research pilot in detail. But before we do so, I would like to probably share a short blockchain one-on-one, which might be helpful. So what is blockchain, right? Most of us, or a lot of people, still think of blockchain and cryptocurrencies like Bitcoin or Ether or Matic as to be the one and same, right? However, that is not quite true. Blockchains are digital ledgers powering cryptocurrency applications from underneath, but blockchains can also power a lot of other applications, such as the one used in our pilot, right? So blockchains are essentially distributed databases, which are sitting across multiple host computers or nodes. And each node owns a complete copy of the ledger content. The core principle of blockchain is decentralization of consensus, where the network nodes agree on an ordered list of transactions to be included in blocks. And the blocks actually are information blocks, and they form a cryptographically linked chain, which is extremely difficult to tamper with, or in other words, immutable, has no mutation that is possible. So through these qualities, blockchains provide a single source of truth for multi-party workflows by providing a secure audit trail of what happened and who authorized it. You often hear that blockchain uses cryptography. It does indeed, cryptography is used in two layers. In the first layer, blockchain uses strong cryptography to verify the authenticity of its user and to synchronize data across its network of nodes. The first layer of cryptography is applied at the node or the account level so that every node has a unique private key. Assets such as either digital currency or digital files owned by a node can only then be moved if the transaction is digitally signed by the node's private key. And the second layer of cryptography happens when multiple transactions are ordered and encoded into blocks, where they are run through a cryptographic hash function that produces a unique fixed size and short string representing all the data. The hash of the previous block is included in the next block's header. And as a result, this hashing process creates a system where any modification made to a past transaction results in changes of the new transactions as well. And as a result, the whole system and the changes become very easily detectable. So all that is very theoretical, right? So let's kind of look at one automotive industry example. So in the automotive industry, we mostly play in the domain of permission blockchains that allows us to invite our ecosystem partners, such as our suppliers, dealerships, and customers, to co-create a single source of truth without any intermediary. So let's look at a simple supply chain use case here. We will follow the journey of a part starting from a tier supplier to the OEM, then to the dealership, and finally to an end customer. And the part is tracked on blockchain using its, let's say, unique serial number barcode, QR code, or any type of authentication and identification technology. It could be also that contactless technology that Ellen described a few minutes ago, right? So each of the stakeholders in the scenario, as you can see, if you follow my cursor, is hosting a local copy of the ledger with the full ledger contents. And together, as I will show, they record the transfer of the part from one stakeholder to another at each step of the journey. So first, the supplier will send a part to the OEM at the end of production, and all nodes in the network will register this transaction in their local copy of the ledger. Next, the OEM will install the part in a vehicle and send the vehicle to the dealership for sale. All nodes in the network will record this transaction as well. Finally, the dealership will sell the vehicle to an end customer, and all nodes in the network will record this third transaction that indicates the customer as the final custodian of the part installed in the vehicle that they own. Please note that this journey is overly simple and doesn't include the third-party logistic flow, which is actually an important use case of blockchain in the supply chain space. But for the sake of simplicity, we excluded them in this sample workflow. And it is also hopefully easy to see that using a system like this, we can track the parts and our products as they move through the different stakeholders in the supply chain. We can track our purchase orders, change requests, receipts, trade-related details, and also verify product certificates. We can also validate whether a particular product meets certain quality requirements and detect issues in real time. And that will be more clearer as I describe the pilot, which is kind of coming back to blockchain for distributed AM. So I will kind of walk us through as the workflow that we implemented in our research pilot called AM Part Passport. Please note that this is mostly a potential future state. Right. So the workflow starts from the point when an AM part is already designed and engineered and ready to be released. The 4DNR engineer shall use an identified 3D software process called Protect to create an encrypted digital supply item, or DSI, containing the final design of the part and all of its associated engineering data that tells us how to build the part. The DNR engineer will also create a license file that defines the serial number format for part identification, as well as the machine material and set of parameters that should be used to print the parts. Then the DSI and the license are moved on blockchain to the next step, where the Ford buyer shall use an identified 3D software process called manage to authorize the DSI for a specific supplier or for a number of suppliers. And this authorization will also include the quantity, the expiry date, and changes, if any, made to the original build parameters. Once authorized, then the DSI and the license are moved on blockchain to the supplier. The supplier may send the files directly to a 3D printer or a downstream distribution phase if they are using additional subcontractors to fulfill the purchase order. So that kind of brings us to the end of step 7, or through step 1 through 7. Now let's move on to the supplier side, right? So the supplier, after receiving the DSI and the license, they will send it to the machine, and the DSI will be decrypted on a secure PC connected to the machine and printed using a third process called Identified 3D Enforce that is running on the secure PC. The machine log is collected in real time and stored on blockchain. And Ford actually requires in this workflow, through the public sections of the DSI, that a set of quality measurements need to be taken at the end of the print job. For sake of simplicity, we just, our quality requirements in this pilot were simple dimensional measurements. And the result of the quality checks are then written on the blockchain for the part serial number with a link to the original DSI that it came from. In that way, a physical part always knows its own provenance on the blockchain. Next, when the supplier is ready to ship the parts back to the OEM, they can use a blockchain smart contract to automatically generate an advanced shipment notice, or ASN, and send it to the OEM on blockchain. The physical shipment is sent to the OEM assembly plant. Then next, around step 13, when the Ford assembly plant engineer receives the shipment, they usually perform another quality check to accept or reject the parts at the shipping dock. Having access to the secure and tamper-proof digital thread makes it very easy for the Ford assembly plant engineer to verify a part using its serial number or any other part identification method and look up all its workflow data, all the way from design to print, using an identified 3D process called Trace that provides a human-readable user interface to the blockchain. The accepted parts are then moved along the assembly line and installed in the vehicle. The installation status and any quality data collected during this time are also recorded on blockchain with the part serial number, which is then linked with the vehicle identity on blockchain for further traceability in the field after the vehicle is sold. It is worth mentioning, though, that this last step of the workflow is real at Ford production environments today, in that we install 3D printed parts in our vehicles, in our plants. We just do it without using blockchain for the traceability of our digital threads, but we did so in our research pilot. So in the next slide, we will take a look at the benefits of using an integrated IoT blockchain solution. Since the transactions on blockchain are stored on a shared ledger that provides record immutability, it basically provides a tamper-proof audit trail for all the processes and quality data associated with each part. Also, since all the digital license authorizations are implemented as smart contracts, the business rules are verified automatically by network consensus. And full visibility of the supply chain is also possible with blockchain, so that the OEM can review which subcontractors were used by a tier 1 supplier to fulfill a purchase order. Last but not the least, keep in mind that blockchain ensures trust and integrity of data once it is stored on the ledger. But it, of course, cannot guarantee that the same for the data coming into the blockchain. In other words, if we store digital garbage on blockchain, then blockchain will help us to store the digital garbage securely, but it cannot really detect or improve the quality of the data that is coming into it. And this is really where the benefit of an IoT integrated blockchain solution shines. With machine integration, we can actually extend the trust boundary all the way to the hardware to ensure that data is collected directly from the machine. Additionally, we can run advanced AI or machine learning algorithms, which on the machines directly or on a secure PC connected to the machine to detect anomalies and also make sure that only quality data is written on blockchain. This last piece of anomaly detection on the machine was not part of our research pilot, but this is something we definitely plan to do research on in the future. So here, we wanted to show a demo of our first pilot that we completed with Identify 3D in 2020. The major components of this first phase involved a standard Identify 3D solution with a FDM desktop printer, a Lalsbot Mini 2. We also used a standard blockchain provided by IBM Blockchain Cloud, and that is integrated with the Identify 3D solution, and an emulated version of Ford quality control process integrated into workflow and tracked on blockchain. The video is 5 minutes long, and it shows the workflow I actually presented in the previous slide. So I'm gonna try and play the video. It doesn't have a video, any audio, but it has some closed caption, and I will also do my best to be a live narrator. So in the first phase, as you can see, the Identify 3D Protect process is being used to create a DSI. We just entered the name of the package and a description. Then for the DSI content, we have the opportunity to add files in both the private and the public sections. We can also add manufacturing policies and choose what particular machine we are authorizing this part to be printed for. We are also choosing the expiry date for the license, right? And the authorized quantity. And finally, we are adding a serialization format for the quantity or the volume that we are authorizing. Now, once the DSI and the license files are generated, we are using Identify 3D process called manage to send or control the distribution of them to downstream managed instances, which are often being run by tier 1 suppliers. So here we are sending the DSI and the license using Identify 3D manage process integrated with blockchain. Then the manufacturing managed process, which is usually running at the supplier side, they are using a very similar user interface to then basically authorize the DSI to one of their machine to print some of the authorized volume. And here you can see the user interface for the Lalsbot Mini 2 printer, which we called Oberon in our workflow. And here we are decrypting the file, the DSI, and going to start the production, and all the machine log will be starting to come in a few minutes. The print job just started. We had authorized 2 volume or 2 parts, so you can see here also that we can track that the quantity remaining is 1, because we just started to print 1 part. If we hit pause, then there will be a pause event that will be tracked and also added to the machine log that will be tracked on blockchain. Here you can see the actual printer in action. When the job is complete, what I call machine log, it has a nicer name, DTL, digital trace log, is generated and sent to Trace. And Trace is the user interface to blockchain. So Trace would write this machine log on blockchain. We just tried to start the second job and then paused it to make sure that we are testing for different plant scenarios on blockchain. And then we tried to start a third job. And if you recall, we had authorized only 2 quantity for production. So the third job was not authorized from the machine. And here you are seeing the user interface for Trace, and which is a human readable format for blockchain. So for a given serial number, you can see that from design to print, the entire digital twin or the digital thread is available for that serial number. And that was the end of this demo. I hope that it was helpful to make certain things clear. Happy to answer questions during Q&A, but for sake of time, I will move us along to end the presentation. So in the next slide, I wanted to quickly mention that in addition to the Lalsbot desktop printer, we also worked on a second phase of the pilot where we migrated our solution to a production grade Stratasys F370 printer. It is not one of those machines being used for production parts at Ford today, but it was still a very good learning exercise to understand what does it take to integrate with a more serious machine than just a desktop FDM printer. One of the primary aspects of this pilot was the machine integration using Stratasys supplied GrabCAD APIs. We have a custom code called Identify 3D Enforce running on a secure PC connected to the printer that is making the GrabCAD API calls. This code also interacts with blockchain and records key manufacturing events such as start, stop, pause, fail, complete, etc. And finally, I would like to end with some lessons learned from our pilot. With this pilot, we proved that with the intersection of different emerging technologies such as IoT, blockchain, computer vision, AI, and machine learning, we can significantly improve AM digital thread security, traceability, and manufacturing repeatability. With the contactless technology that Ellen described, we also proved that part authentication and counterfeit detection is significantly improved. Some of the challenges that we have that we need to address in our future work are first of all is the ecosystem challenge. Blockchain is still an emerging technology, and mapping and onboarding our entire supply chain on the same blockchain network is not a trivial task. Current supply chain incentivization techniques are not adequate for this kind of disruption. We do need to think about new types of incentivization techniques, such as blockchain-based micropayment, real-time settlement, and so on. We also need to create integration with many more 3D printing platforms and bring traceability to a lower level, that is between stations in a manufacturing line. Today, this traceability is achieved at Ford with a piece of paper called Rider that physically travels with the part from station to station. We would like to modernize this by digitizing our Rider on blockchain. Also, our pilot with Identify 3D developed a solution to serialize only one part per build tray, which is not a very realistic scenario for production environments. Therefore, we would also like to investigate a solution for serializing multi-part build trays and also for supporting multiple network stations or machines from the same secure PC. And with that, I think that brings us to the end of our presentation, and we would be happy to take any questions.
Thank you. Thank you both so much for sharing your work with us. One thing that someone also asked is this published? Is there a place that people can read about this work?